This is a review of polar molecules, intermolecular forces, and boiling point. So first, let's take a look at what is a polar covalent bond. So what we have here is a periodic table where we have shown that electronegativity increases as we go from left to right across the periodic table, with fluorine being the most electronegative of the elements. As we go down a table, the electronegativity decreases. So polar bonds form when we have two nonmetals with different electronegativities. The greater the electronegativity difference, the more polar the bond. So a carbon-fluorine bond is going to be more polar than a carbon-nitrogen bond. So if we look at nonpolar covalent bonds, that would mean that we have two identical molecules, two identical atoms, and they're going to be sharing the electrons exactly equally. If we put together a non-electronegative element, relatively speaking, hydrogen with the electronegative one, the electrons are going to be pulled to the chlorine, the more electronegative end of the molecule, and we'll say it has a dipole moment. Now, an extreme case is when we have a huge difference in electronegativity, and this is when we have a metal plus a nonmetal. And in this case, we see complete electron transfer, and we have the ionic bond, which is the attraction between the positive cation and the negative anion. So if we have polar covalent bonds, then it is possible to form polar molecules, or molecules with a dipole moment. So for example, here we have chloromethane. Chlorine is highly electronegative, so the electrons are getting pulled towards the chlorine, so we have that partial negative charge, and so we have a net dipole moment, and we say that this is a polar molecule. Sometimes we can have more than one polar bond, and in the case of ammonia here, we have 1, 2, 3 polar bonds. And if we look, all the polar bonds are ultimately pulling towards the top of the molecule, so that we say that this molecule has a net dipole moment. So the individual bond polarities do not cancel. Now let's take a look at water, where we have two polar hydrogen-oxygen bonds as shown. The polar bonds reinforce each other. In other words, the polar bonds do not cancel, and the molecule is polar. Now, it's possible to have polar bonds and yet the molecule not be polar. In the case of carbon dioxide here, we have two opposing polar bonds and the entire molecule is not polar. So the electrons are getting pulled equally to opposite ends of the molecule. In the case of carbon tetrafluoride, we have the same thing. All the individual bond polarities cancel, so the molecule does not have a dipole moment. The molecule is not polar. The polarity or non-polarity of a molecule is going to have an impact on the intermolecular forces between a molecule. Intermolecular forces are the attractions between molecules, and the molecules are held together based on electrostatic forces. So we're going to review the types of intermolecular forces in pure substances. We have London dispersion forces, dipole-dipole forces, and intermolecular hydrogen bonding. And let's go through them. Now, why do we care? Well, it's because intermolecular force strengths determine melting and boiling points, and we're going to concentrate on boiling points. If we have liquid nitrogen, and this is going to be at very cold temperatures, the molecules are weakly attracted to each other, and we have a liquid phase. But at higher temperatures, the intermolecular forces are overcome, and the nitrogen becomes a gas. So let's take a look at the intermolecular forces. We'll go from weakest to strongest. London dispersion forces, this is when you have non-polar molecules. This is the only force that exists, but it actually occurs in all molecules. So this is based on total electrons. Okay, And all molecules have, and we're going to call these LDFs for short, London dispersion forces. The AP exam will know what you're talking about if you use London dispersion forces. So we have temporary attractions because the electrons are moving all over the entire molecule, and so we have temporary dipoles, and this is your London dispersion force between the temporary dipoles. The London dispersion forces increase as the polarizability of the electron cloud increases. So the London dispersion forces are going to be greater in molecules with more total electrons. And let's take a look at just the total electrons here. Fluorine has 9 electrons, so in total, a fluorine molecule has 18 total electrons. Whereas if we can compare it on the other end with iodine, iodine has 53 electrons, so that would be a total of 106 electrons in the molecule. So iodine, if you think of it as a cloud, has a great big cloud, whereas fluorine has a much smaller cloud. So this is a much more polarizable electron cloud on the iodine. As IMFs increase, boiling points and melting points increase, and you always want to add this phrase here, more energy is needed to overcome the IMFs. Now, let's take a look at a subtlety with London dispersion forces. We have C5H12 is the formula for both of these molecules. However, one is a straight chain molecule and the other one has branches, but they're both C5H12. If we look, pentane has a boiling point of 309.2 kPa versus 2,2-dimethylpropane, 282.6. The reason is that this is a long molecule, so the electrons can vary more where they are along the entire molecule. So this long chain is more polarizable. Hence, it has greater London dispersion forces. So greater LDFs. Okay, so all molecules have London dispersion forces. If a molecule is polar, then it has dipole-dipole attraction. So this is only for polar molecules. The more polar the molecule, the greater the dipole attraction. So here we have 4 different substances. We start off with propane right here. This has only carbon-hydrogen bonds, so it is essentially nonpolar. And we see that its dipole moment is 0.08 and the boiling point is 231. Notice that all of these have almost the same molar mass. It's very close, so the number of total electrons is not very different. Now, we get to methyl ether here. Let's put in our 2 electrons. Now we've got electrons being attracted towards the oxygen molecule. Remember, you're going to be bent around this central oxygen here. So this molecule is slightly polar, and we can see that the boiling point increases. When we have chloromethane, now this molecule is very definitely polar. It has a dipole moment of 1.90, and the boiling point goes up again. And then we have the nitrile group where we have the very polar carbon-nitrogen bond, and so this molecule has a high dipole moment and the boiling point increases again. So as the dipole moment or polarity increases, we also see that the boiling point increases. Hydrogen bonding is the last type of intermolecular forces between pure substances. It's going to be between a hydrogen atom bonded to a very electronegative element, O, N, or F. I use the phrase H-NOF. Okay, so hydrogen has to be directly bonded to either nitrogen, oxygen, or fluorine. So here is an example of a hydrogen bond. Note that this is not a hydrogen bond. This is a covalent bond. Covalent. All right. So this is water showing the hydrogen bonding. On this side, we have the ammonia showing the hydrogen bonding. The hydrogen bonding explains why water has such a very high boiling point. It can form up to 4 intermolecular hydrogen bonds on every water molecule. Let's take a look at intermolecular hydrogen bonding in another molecule, methanol, CH3OH. So here is a methanol molecule, and you can see the little red intermolecular hydrogen bondings between the molecules of methanol. So let's circle the hydrogens that are capable of the intermolecular hydrogen bonding. This hydrogen, this hydrogen. Now, if we take a look at methanol, I want you to be very clear that it is only this molecule, this atom, that can participate in the intermolecular hydrogen bonding. These hydrogens are not directly attached to an oxygen, a nitrogen, or a fluorine, so there is not going to be any intermolecular hydrogen bonding. Okay, let's take a look at a series of molecules, and we've got a graph here that shows the normal boiling point, that means at 1 atmosphere, versus the molecular mass. And the question is, why does ASH3 have a higher boiling point than PH3? So arsenic trichloride versus phosphorus trichloride. Well, as we go across the molar mass, the London dispersion forces increase. So the arsenic trichloride has more total electrons than PH3, so ASH3 is more polarizable. This is a very important term. Thus, arsenic trichloride has greater LDFs and more energy is required to overcome the stronger LDFs. So that's very clear cut, just the London dispersion forces. Now, if we look at this series, NH3 has a higher boiling point than PH3, even though PH3 has more total electrons. So the question is, why does NH3 have a higher boiling point? Well, now what we're looking at is the hydrogen bonding. So anything in this yellow square here is capable of hydrogen bonding. So NH3 is capable of intermolecular hydrogen bonding. So NH3 can form intermolecular hydrogen bonds, IHB. Now remember, if you're going to use an abbreviation, identify it as you write. Dipole-dipole attractions and LDFs. PH3 molecules are only attracted by London dispersions. Thus, more energy is needed to overcome NH3's greater IMFs. We're going to talk about one type more of intermolecular force. That's called an ion dipole force. It's the attraction between an anion or a cation and polar molecules. We're going to return to these more when we discuss. Let me show you a particular example that will be important to us. It's ion dipole forces that cause water to dissolve ionic compounds. So what we're looking at here is the negative end of the water molecule being attracted to cations and the positive sides of a water molecule being attracted to anions. Okay, let's do a summary on intermolecular forces. We have ion dipole. These occur between ions and polar solvents. We have dipole-dipole. These can only occur between polar molecules. London dispersion forces. These occur between all molecules. And then we have hydrogen bonding, which only occurs when we have oxygen directly bonded to O, N, or F. Now, even though London dispersion forces are the weakest, they can be very strong in large molecules. For example, for C12H14, It has a higher boiling point than H2O because of the huge differences in LDFs, despite water's hydrogen bonding and dipole-dipole attractions. And I just noticed my formula on that is wrong. It should be C12H26. My apologies.